continuing with the experiments in modern communications, electronic communications, I would like next to do experiment 37 out of the book by Beasley and Miller. That's this modern electronic communications lab manual. And the specific circuit that we're using is this one. It is a mixer, the purpose of which is to demonstrate how you can up convert or down convert a signal. In other words, the idea is that you have a particular frequency that is coming in with some information impressed on it and modulated in some form, and you want to convert that frequency to a different frequency for whatever purposes. And a circuit that allows you to do that is a mixer. In this particular case, the recommended mixer is the MiniCircuits ZP3. And we will do some experiments with this mixer, but I'm also going to be using a different MiniCircuits mixer, the SBL11. I don't know if that's readable or not, which is a printed circuit board version. And as I pointed out before, these connector versions of circuits are much more expensive. I think this one is about $40, whereas this one is about, I don't remember, but way less than 20. And this one goes to 2,000 megahertz, whereas this one only goes to 400. But before we look at the specs and get into the experiment itself, I think it might be helpful to review a little bit on mixers themselves. Since I'm putting these videos together for an audience that spans graduate electrical engineering students through experimenters and amateur radio operators who perhaps are far less interested in the mathematics, I'm going to try to strike a balance by mentioning the mathematics but not dwelling on it, but basically sticking to the characteristics. And in order to do that, I think it would be helpful to discuss the differences between linear and nonlinear circuits. So let's start out just considering a resistor, where the current is the voltage divided by the resistance. In my case, I'm going to be using voltage in volts and current in milliamps. Consider two cases, a 1000 ohm resistor, 500 ohm resistor, and here is the voltage and current that you would get from that. That is a linear circuit, and in a minute when we look at the curves you'll see why. If you contrast that, however, with a diode has a voltage current characteristic that is basically an exponent. That is, it's the base of the Neperian log system E, the so-called natural log system, to some exponent. And the exponent is related to kT over Q. K is Boltzmann's constant, T is temperature, and Q is charge. We won't get into the physics. In fact, this is a very simplified equation, and the actual physics are rather complicated. But nonetheless, you can see that this is an exponent. In other words, it's something multiplied by something some number of times. So now let's look at what that means in terms of the curves. On the left, you see, is an IV characteristic for a 500 ohm resistor and a 1000 ohm resistor. Notice they are straight lines, and the only difference between them is the so-called slope. So a 500 ohm resistor has a higher slope than a 1000 ohm resistor because the current goes up faster but nonetheless they are very linear. In other words, you can simply project this out as far as you want. The diode, on the other hand, looks like this. And here I have not shown particular values of voltage because it depends on the material and other things. But in general, as you begin to apply voltage to a diode, the current goes up. But as you increase the voltage, the current goes up faster. In other words, it is an exponential curve, which eventually reaches fairly large values. And at that value, it's a sort of limiting voltage. For example, a silicon diode will normally have about 0.6 of a volt. And if you raise the voltage very much above 0.6, the current goes up a lot. A germanium diode is usually down around 0.2 of a volt, and I'm just using approximate numbers here. And once again, this is all at room temperature. So why do we care about all that stuff? Well, the reason is because, and here I do have to introduce a little bit of trig for those of you with more math. This isn't going to be a problem. For those of you without, please bear with me for a second. I'm only going to illustrate a point. I'm not going to try to teach you trigonometry. If you add two sine waves, what you get is a product of the two sine waves. But notice it's all one wave. Now, it may not be quite so clear here, but the point is that there is only one term on the right-hand side. What you will get is a mix of the two waves themselves, but you do not get any additional products. However, when you multiply a sine wave by another sine wave, you get different terms. In this case, this is the cosine of x minus y minus the cosine of x plus y. Now this assumes that you have a perfect multiplier. Notice the difference. This is addition. That's what happens in a resistor network. You can add a bunch of signals together using resistors, and all you get is the sum of all those signals. If, however, you apply two sine waves to a diode, because of this nonlinear characteristic, you get multiplication. Now, the actual frequencies you get are a lot more complicated than this, but we're going to focus only on two of them. One is the difference frequency. In other words, if x is in a particular frequency and y is a particular frequency, and we can talk about that, but not in this video. The sum frequency and the sum frequency and the difference frequency will appear in the output. That is what a mixer is all about. In other words, it's about producing additional components in addition to the two signals that are being applied to its input. One of them is the difference in the frequency. The other is the sum of the frequencies. So in other words, you apply two signals, you get four out. This is the MiniCircuits datasheet for the ZP3. This is a packaged mixer with B and C connectors that operates from approximately 150 kilohertz to approximately 400 megahertz. Now, when I say approximately, there is a chart that shows the frequency characteristics of the particular mixer. But understand that, like any electronic circuit, you can get some useful results below 150 kilohertz and some above 400 megahertz. It's just that the manufacturer won't tell you what the characteristics are. They won't guarantee the characteristics outside that range. So what is this particular mixer? Well, similarly, if you saw the earlier video on the pin diode attenuator, you're familiar with this basic circuit. There is, in this case, the L on the left means this is the preferred input for the local oscillator. That's one of the frequencies. And on the right is the preferred input for the RF, or radio frequency. That's the signal to be transformed. In other words, this is the incoming signal with intelligence. This is a locally generated signal, the purpose of which is the signal gets mixed or switched, depending on your point of view, by these diodes and produces an intermediate frequency at this point. Now, for reasons we won't get into here, this is a balanced mixer, and that helps to balance out certain of the components. So for example, the RF signal is much reduced, as well as the local oscillator signal much reduced, so that basically at the I signal there is the sum and difference are the major components, and the input RF and the local oscillator are much reduced, and we'll see that on the spectrum analyzer in a little bit. So here is the MiniCircuits mixer on the right over here, and we are putting in two frequencies. Frequency 1 is 21 megahertz and frequency 2 is 20 megahertz, as you see there. The 20 megahertz is at plus 5 dBm, and we'll talk about why that is in a second. Frequency 1, the 21 megahertz, is at minus 20 dBm. Those signals are coming from the HP generator over here in the case of the 5 dBm signal, and the minus 20 dBm signal is coming from this Siglent function generator. On the Rigol spectrum analyzer, you see the 1 megahertz difference frequency. That is 21 and 20 produce an IF of 1 megahertz. So let's measure the peak of that. And you see it's 1.033 at minus 35 dBm. But let me show you something that is rather important when you're doing these kinds of measurements. Right now, the resolution bandwidth is at 30 kilohertz. What I'm going to do is lower that to 10 kilohertz. You may notice that as we do that, the peak detection falls off from the actual peak. So let's redo the peak detection. And now you see you get a very accurate frequency measurement. That is, it does exactly measure 1 megahertz, which the generator that's putting out the 1 megahertz, or the 20 and the 21 megahertz, are both very stable and accurate. So you would expect to get a very accurate IF frequency. But if you use too wide a resolution bandwidth, the peak detection circuitry in these spectrum analyzers will they have a lot of variation in them. So only if you produce a very, very sharp spike are you going to get an accurate measurement of the frequency. Now what we're going to do is we're going to move out, and we're going to do measurements of a number of frequencies that are shown there that are above 1 megahertz. We'll look at 2 megahertz, but only cursorily, and then we'll look up at the components at 20, 21, and at higher frequencies. The sum, of course, will be 41 megahertz, so we'll want to go to at least 44 megahertz. And the basic idea there is to understand, if you are doing this experiment in a college lab, you already know that one of the purposes of this exercise is to learn about the order of harmonics and the order of mixers, because if you're designing a mixer, you would like the order of the IF to be as low as possible. That minimizes phase noise and other things that we're not going to talk about here. but nonetheless it's an important design parameter. So what we're going to be doing is looking at the order of the, that's this column here, of the various frequency components, and then we're going to be measuring the actual level of those harmonics, of those frequencies. You see the peak at the 41 megahertz frequency, which is the sum of 20 and 21. It is reading minus 26.4 approximately dBm. We're then going to go one peak to the left, and this is the 39 megahertz, and it's reading about minus 38 dBm. I'm going to go one peak to the right again just to see if I can get, well, it's not reading, this one is not tall enough to show up in the peak table, but this is the 40 megahertz, which is the second harmonic of the 20 megahertz signal, and it shows that there is some leakage through of the second harmonic of the local oscillator. Now we'll go one more peak to the left, and this is the 21 megahertz signal, and in other words that is the other oscillator. Then we will go one more peak to the left from there, and we get the 20 megahertz, and it's about 59 minus 59 dB. And here are the figures that I got for these four frequencies, which were the highest peaks that showed up on this particular one, except for the peaks down around a megahertz, which we'll look at in a second. You may notice that the calculated levels of the 39 and 41 megahertz, that is the second harmonic, or more appropriately the fourth order and the second order, are very close to the calculated values. The calculated value for 20 megahertz, this was not calculated, it came out at 60 dB minus 60 dBm, and the 21 megahertz came out at minus 34 dBm, even though it was calculated to be minus 20 dBm. And we'll talk about that more in a second. But first, I want to raise the level of the local oscillator to the specified 7 dBm that MiniCircuits asks for. Now understand, what we've just done is the experiment that is shown in the Beasley and Miller lab handbook. But they operate at 5 dBm, partially because of the limitations of some of the test equipment in the labs at the time this experiment was put together. But we can go to 7 dBm, which is the MiniCircuits specified value, and then we will take those readings again and see if they change any. Well, as you can see, the readings did not change substantially. The minus 60, which was the zeroth order, in other words, the 20 megahertz directly through, is now reading minus 57. The 21 megahertz went from minus 54 to minus 55. So this one went down, this one went up slightly. And the 39 and 41 went from minus 38 to 37, and minus 26 stayed at minus 26. So now let's go down and look at the 1 megahertz. And now we have changed the spectrum analyzer to have a start frequency of 500 kilohertz and a resolution bandwidth of 3 kilohertz, a stop frequency of 3 megahertz. And this is the 1 megahertz difference signal, or intermediate frequency. And as you may be able to read here, it's at minus 26. We can make some observations about this. What this tells us is that this mixer is actually better than the one that was used originally by the person who prepared this particular lab exercise. But nonetheless, the important thing is to recognize that the first order or second order term, that is the 41 megahertz, the sum of the two, as well as the first order difference frequency, are substantially the same, minus 26 dBm. Now, given that we are putting in minus 20 dBm of signal, this means that we're only getting a 6 dB conversion loss, which is exactly what MiniCircuits specifies for this, and you can't frankly get any better than that with a passive mixer, because you're dividing the signal. Essentially, you're losing 6 dB just from the fact that the input frequency is being split into two new frequencies. So 6 dB is the best you can hope for with a passive mixer. So we're putting in minus 20, we're getting out minus 26. Once again, shows us that this is a very, very good mixer, at least as passive mixers go. So I'm going to wrap up this particular experiment at this time. I hope you've enjoyed this. I hope you get results similar to the ones I got, and that you, more importantly, you've learned how to characterize and measure the characteristics of a mixer. Look forward to seeing you in a future video.